Welcome everyone. It's my pleasure to welcome Kira Goldner. Kira is a PhD student at University of Washington, and Kira works on algorithmic mechanism design, among other things. And today she's going to tell us about the FedEx problem. Kira.
Thanks. Okay, so this is joint work with Amos Fiat, and Karlin, and Elias Koutsoupias. Okay, so the setting we're talking about is where you have a customer who has a package to ship, and the customer has some value of how much it's worth to them to have the package shipped, and she has a deadline that she needs it by, and she's indifferent if it arrives early. She just wants her package received by the deadline. And this joint distribution on the value deadline pairs is known by FedEx. And so what they want to do is they want to maximize their revenue by offering a discrete set of shipping options to try and segment their market and extract revenue from the people with the different deadlines. So the question is, if you're FedEx and you know this pair distribution, what is the optimal thing you can do? In this talk, I'll be talking about a single buyer, which is equivalent to, yeah?
Sorry, the deadline is when it's shipped, not when it's received?
It's when it's received, but we're just going to talk about the deadline. Yeah. Assume it's immediate. Yeah.
Assuming
Right.
time is zero.
Okay.
Right. Well, you can assume that when it's run, that's when everything is shipped and it's received by the deadline. I might mix up those words throughout the talk. Speaking of which, I might also, when I say like day D, I'm referring to customers with a deadline of day D, or like the shipping option to be received by day D. Okay. So we have a single customer, or we have unlimited supply and many customers coming from the same distribution, but it's probably easier to just think about a single customer. Okay. So other applications, we're calling this a FedEx problem, but it's applicable beyond just FedEx. For example, it was originally motivated by Bitcoin, where you have customers submitting transaction fees and they want their transactions embedded in a block, and they want it done within some timely manner, some number of blocks. You can also imagine that it's some other quality of service. For example, if you're buying an internet plan and you want a certain speed and you don't really care if it's faster than that, you just want to make sure you're at least getting your speed. Or you're buying a car and you have some feature that you want, like a GPS or a backup camera, and they sell the base model and all the various upgrades. And so you want to get an upgrade that at least has whatever your demand is, like a GPS. So this is any setting where there's a time sensitivity or a quality of service constraint. Okay. Problems clear? Okay. So we're in the Bayesian setting where we have this cumulative distribution of the joint value deadline pairs, and you can break this down into the marginal distributions for each possible deadline and the probability of drawing a customer with that deadline. And our only assumption, just for like nice continuity, is that these marginals, Fi, are atomless and strictly increasing. There are no other assumptions on the distributions.
Sorry, what does it mean for something to be atomless?
You don't have any point masses. Yeah. Okay. And for now, we're just going to talk about it being in some bounded range 0 to h, but it can be extended to 0 to infinity. Okay. Cool.
What is h again?
What is, sorry?
What is h?
H, it's just the upper bound. Just assume
some
it's in
upper.
some 0 to h range. But what I'm saying is we're going to talk about that for this talk, but it can be extended to infinity.
Oh, okay.
Yeah. Okay. Cool. So let's just talk about the simplest possible setting. What if there's only one shipping option? Everybody wants one-day shipping. What is this object? This object is a revenue curve. What it does is it maps prices that you could set for shipping to expected revenue. And so some point on the curve is just the price times the probability that a customer is willing to buy at that price. And so that's what this graph is. And we're going to be using them a lot. So I want to make sure you understand what this graph is. Okay. So for example, this is how you would write it out using the distribution. And I just want to point out that this is like a ridiculous curve, and it's just a cartoon curve. It's not created from a real distribution, but it will illustrate nice points throughout the talk. Okay. So what's the best thing to do in this setting? You're given this revenue curve. How should you sell just the one-day shipping? Yes, you should just pick the peak, and that's the optimal thing to do. Does that make sense? It's the most revenue you can get from setting price. Okay. So now what if we have two different options? we have one-day shipping. These are all the people who want their package in 1 day, and these are all the people who want their package in 2 days. Using their marginal distributions, we construct their revenue curves. What could we do to sell the shipping?
You can use two options, I guess.
Yeah, so the best thing to do is just to pick the best price for 1-day shipping and the best price for 2-day shipping. Just pick the peaks on each curve. And in this case, that is the best thing to do. When they're decreasing, the best prices are decreasing, that's the best thing to do. This is optimal in this case. However, if you have curves like this and you try to do the same thing, then you wind up having a cheaper price for 1-day shipping than for 2-day shipping. What's the problem with that is that we're not actually getting the revenue that we're reasoning about. So here, we're reasoning about getting revenue from people who want their package in 2 days, paying for 2-day shipping. But if 1-day shipping is cheaper than 2-day shipping, they're going to buy 1-day shipping. And so it's not just that they're deviating, it's that we're not correctly reasoning about the revenue. Okay. So one example, so you may say, like, maybe this is ridiculous that you would have the best price being cheaper for 1-day shipping than for 2-day shipping. And I want to say we don't want to make that assumption because, first of all, it's a very strong assumption to say that the reserve prices are decreasing or that the distributions are stochastically dominating or whatever. And moreover, like, we can come up with a silly example as to why they might not be positively correlated. So assume it's your friend's birthday tomorrow. You'd like to send them a package. But if 1-day shipping is exorbitantly expensive, it's not that important to send them a birthday present, as opposed to if you're a surgeon and you're conducting open heart surgery in 3 weeks, it's a little bit more important that your equipment gets there by your surgery. So in the case where it's more important to get your package there, you might even take the time to plan ahead. So here's just like a silly example as to why they may not be positively correlated and why the distributions might not have the decreasing reserve prices. Okay. So this was the setting we were in. And we need to reason about how to properly get revenue in this case. So a quick reminder for those of you who don't think about this all the time, what the revelation principle says is if that we have some optimal auction. This is our optimal auction. And we have bidders are taking their information, their value deadline pairs, and they're applying some strategy to them to report something else to the auction. And then the auction, has some allocation and payment rule. That we can, without loss of generality and without any loss of revenue, create an auction around it that it's in their interest to report their true information, because what we do is we take whatever they report and we apply their strategy for them. And then we just output the exact same outcome. And so if it's in their best interest to report their strategic bid in this gray optimal auction, then in this auction it's in their best interest to report their true information, and it's still optimal, but it's also incentive compatible. Okay, so what that means is without any loss of generality or revenue, we can require that people are incentivized to report their true information. Okay. So what's the problem we're trying to solve? We want to maximize our expected revenue from customers with each deadline. Here's where I'm saying day instead of deadline, but I mean the same thing. We want customers to report both their true value V and their true deadline D over any other value or deadline. These are those incentive compatibility constraints. And we also need the allocation rule to be feasible. It's a probability of being served, and so it should be in 0 to 1. Okay. So this is a lot on a slide. The point of this slide is to tell you that many people are very interested in multidimensional revenue maximization. There has been so much work done on it. And these are all like really impressive results. Most of the work is in approximation. When we talk about a lot of the work in revenue maximization, they are constant factor approximations. Our list of optimal auctions is much shorter. I'm not claiming this is a complete list, but it's close. The first thing is just the single item setting. So that's not actually multidimensional. That was completely resolved in 1981. Then there's a result that says, basically using linear programming, that we could compute the optimal thing in polynomial time. But it's not an exact characterization. So the next several things are very, very specific settings. So for example, 2 parameters, each distribution is uniform 0, 1, and there's quadratic utility. These results are saying that for some very specific setting with very simple or restricted distributions, like single crossing or uniform, then we can characterize the optimal auction in these settings. This is just the prior work. Then the next bunch of results are where we say we like this mechanism and under what what restriction on the distribution, is this the optimal mechanism? So this is a list of things we know about optimal mechanisms. This is all approximation, and it's a very short list. That's the point. They're very impressive results. I'm not saying they're not. It's just still a very short list, and so we still have a lot to learn about this. Okay. So the point is our problem is also multidimensional, partially because there are these two parameters, value and deadline. Also, you can view it as a special case of correlated unit demand, where you want one type of service. You just want your one package to be shipped by some deadline, and your value for the first D deadlines is V, and after that it's 0. Okay. So what do? We give an optimal auction for this setting. We don't place any restrictions on the distributions. Okay, what does this auction look like? Every day has a randomized price. What will happen is the customer will, knowing the distributions of the randomized prices in advance, choose a shipping option they want to buy, I, and then the randomized price will be drawn for that option, and then they get to choose whether they want to buy it or not. So maybe that randomized price will be more than they're willing to pay, but they never have to pay anything they're not willing to pay. But they do have to commit to which shipping option in advance. They can't then change their mind and say, I want to buy this other shipping option.
Shipping option just means 1 day shipping, 2 days.
Exactly. Exactly, yeah.
But this seems to be in the opposite direction of the FedEx problem, right? Where people first go with what they want. I mean, you show me the option and I will choose. But here now you're saying, like, you first show, like, I mean.
So what you see in advance is you know the distributions of the randomized prices, right? You know all the possibilities of what the price is. Was that your question, that you don't know the prices?
Yeah. Am I understanding correctly? But that's what is written in this slide.
In reality, people know the prices for different options in advance.
Right, but in reality, it's a pricing, and this is a randomized pricing. So in this case, you know the distributions of the randomized price, and then you commit, and then the random price is drawn from the distribution, which you knew in advance. So you, like, maybe it's like with probability 2/3, it'll be $3, and with probability 1/3, it'll be $6 for 2-day shipping, and 1-day shipping is $5. And you see that, and you say, okay, I'm gonna buy 2-day shipping, and then it happens to be $6, and maybe you regret it and wish you'd buy 1-day shipping, but you knew the chance of it being $6 in advance.
So the customer knows the distributions in advance.
Of the prices, yeah.
Can the customer come again and show again?
Yeah.
No.
Exactly.
No, this is a one-shot setting, but that's definitely an interesting question, yeah.
Ask his sitter to come.
So here's another setting that like might make more sense is in the car example. Like when you go to buy a car, you walk into a lot and you don't know what they're going to tell you how much a car costs, and you have to take it or leave it, right? You don't just So like maybe with FedEx that makes less sense, but this is like a one-shot example with a randomized price. Yeah.
Can you also have deterministic pricing but randomized allocation if you don't care about
Yeah. Yes.
explicit
Yeah. Exactly. Yes.
Sorry, could you repeat what you?
So the question was, can you have deterministic pricing but randomized allocation? And the answer is yes. It would be like definitely pay this price, and then with probability 1/3 your package will get shipped, and with probability 2/3 it won't.
Oh, I see.
But instead, what? Right. So we prefer the randomized price because this way you never pay a price you're not okay with. So it's clear that a lot of people in this room are like, what is this mechanism? And maybe you likely wouldn't want to use it in practice, but first off, it's still interesting to understand. But secondly, there are companies that use this mechanism in practice. No,
Yeah.
I just want to be clear on that. For example, like Priceline, when you buy a ticket on Priceline, the allocation is randomized, right? You pay a price, you don't know exactly which ticket you're going to get. Yeah.
So the buy, no buy decision is final. There's not a
No,
chance to
well, I
repeat
mean,
the transaction.
They don't do that.
Right. This is a one-shot mechanism. Yes.
How do you enforce that? I can generalize.
How do you enforce that? Well, if you have a single customer, it's clear when it happens, right?
So one question, why
Smart
is the fact that the customers knows the price distribution in advance doesn't matter?
Well, it's what makes it incentive compatible is that they can reason about what the right thing to do, and what we're going to require a mechanism to do is that the shipping option they choose is the same as
So
their
you're saying the
deadline.
customers rational, so they need to reason about the distributions and probability, etc.
Right. Yeah.
Well, okay, I might be reading like too far into the analogy, so cut me off if you need to.
Okay.
But in this case, is it also an option for like? Have you thought about if everybody is applying this sort of thing, and if I as a customer know the distribution, then like at a car dealership, I can just go to another dealership and
Right.
randomize
So,
draw. It's not
so one more time, we're in the setting where we have a single seller,
Right,
and it's
okay.
one shot.
Gotcha.
Yeah.
Okay.
Alright.
Yes, these are all real considerations, and like considering those problems is super interesting, like a dynamic problem or multiple
Right.
sellers. But this problem,
Right.
which is the first in this space, is the simplest case. Yes.
And you know that deterministic mechanisms won't be good.
Well, this mechanism in some cases is deterministic under certain conditions. Like sometimes instead of setting a randomized price, you'll just set a price. How does the deterministic mechanism compare to the optimal mechanism? We don't know.
Actually, you can simplify this problem so the distribution is just a direct delta function. Then you have a deterministic pricing.
Well, we can solve for the optimal
Right.
deterministic pricing, but what is the gap between the deterministic pricing, the best deterministic pricing, and the optimal pricing? We don't know. That's an open question.
What do you mean you can solve for the optimal deterministic pricing?
We understand what you would do to solve to compute the optimal deterministic pricing.
So you mean there's a polytime algorithm to find optimal price?
I'm not sure if it's polytime, but certainly we know how to compute it. And it makes it. Maybe we should talk about this offline. It makes more sense after you've seen the rest of this because it's similar to the optimal. Yes. Okay. Cool. Great. Okay. No more questions. Okay. Right. So this is our result. Is that the mechanism looks like this, and now I'm going to show how to solve for it and why. Okay. So we said that we can require incentive compatibility. So here's a little refresher of single item auction theory, in case you don't remember. We know from single item auction theory, here we have an allocation rule. What this allocation rule means is that if you bid below P lower, then you're not going to get anything. You're not going to get your package shipped. If you bid between P lower and P upper, then you get your package shipped with probability 1/3. And if you bid above P upper, then you definitely get your package shipped. So this is the randomized allocation. Okay. So what we know from single item auction theory is that the payment is determined by this in order to be incentive compatible. The payment should be the area to the left of the curve. So if you bid P, then your payment is going to be the area to the left of the curve, which is 1/3 P lower here. Okay? I'm not going to motivate this. I'm just going to tell you it's true. Okay. What's more is that utility is also explicitly determined by the allocation rule. Your allocated value, because you're receiving it with probability 1/3, and your value is P if you bid P and it's incentive compatible. So this is your allocated value minus your payment. That's your utility. So your utility is just area under the curve. So all I want you to take away from this is that these things are explicitly determined. We know this from way back in single item auction theory, and your utility is area under the curve. Okay. So our incentive compatibility constraints are that.
I'm sorry, can I ask a question about
Yes.
the previous slide?
Yes.
So does that mean if I pay more than P but less than P ceiling, P upper, that I have paid more money for the same probability of shipment, but your claim is I've extracted more utility?
So this axis is your bid or your
Right.
or your value when it's incentive compatible. It's not your payment.
Oh,
Your
I see.
payment is the area to the left, which is equal for all of those.
Oh, I see. Sorry. Okay,
Yeah.
you did say that.
Right. So your allocation will be the same as your payment.
Yeah, I
Or
misunderstood.
when your allocation is the same, your payment's the same. Yeah. Okay. Cool. So then the other thing we know from single item auction theory is that the allocation rule needs to be monotone weakly increasing. So now that takes care of reporting your true value. How do you deal with reporting your true deadline? Well, what we can observe is that we can, without loss of generality, say that your package will be received on the deadline you want it received by. And so you would never report later because then you're not willing to tolerate that. And so we can just require that you want to report your true deadline over 1 day earlier. And if that's true for every deadline, then you never want to report earlier at all by transitivity, right? Okay. And so how do we do this? We just say that you should get more utility for reporting your true deadline than for 1 day earlier. And since utility is area under the curve, then there should be more area under the day 2 curve, the pink curve, than under the green day 1 curve at every bid, at any possible value you could have. You should get more utility for reporting the later deadline than the earlier deadline, and this way people with the later deadline will report their true deadline. Okay, so just an example of that is here we have a price of P1 on day 1, the green curve, and P2, which is lower on day 2, and here there is clearly more area under the pink curve at every point than under the green curve. So this is okay by our incentive compatibility constraint, right?
So this is enforcing the strict ordering on the set of that very maybe second slide you showed us where you had the day 1 and the day 2 curves, but they were flipped and
Right.
we're never going to realize that value as the
Right.
seller.
So this is exactly the
That's
constraint
right.
that if we enforce it, then we're correctly reasoning about our revenue.
Got it.
However, if you flip it, which was the problem in that case when the price for day 1 was lower, then clearly there is more area under the green curve than under the pink curve, and therefore we are violating this constraint. I know you guys know what area under a curve is, but just understanding how utility works in with the allocation rules. Cool. Okay. So one other thing I want to point out is that another way to talk about allocation rules, every monotone weakly increasing allocation rule, which are the type that we are constrained to, can be decomposed into a convex combination of prices. It may not be a finite convex combination, but still can be decomposed into a convex combination of prices. And likewise, every convex combination of prices will make a monotone weakly increasing allocation rule. So we can just verify this, that if you bid less than P lower, you get 0 plus 0. So this is the same. If you bid between P lower and P upper, here you're getting 1/3 times 1 plus 0. This is 1/3, right? And here we're getting 1 because we have 1/3 times 1 plus 2/3 times 1. So this allocation rule is just breaks down into these two prices. And these are prices because it goes up at this specific price, and the area to the left of it is that price, right? This goes with everything we've said so far. Did that make sense?
Yes.
Okay. So the point is that if we go back to our revenue curve, which in this case is like this black wavy thing, we can actually implement the revenue along this blue curve here. And so this is what we call the ironed curve in value space, which is the least concave upper bound on the curve, because we can take any convex combination of points and thus achieve the revenue here by just implementing the allocation rule that says, do this with this probability and this with this. Does that make sense?
That's cool.
So now we know that we can get more revenue than just on the revenue curve. This comes up if our distributions are kind of wonky, which gives us these wonky curves, and then we're going to use the ironing. And I just want to point out that this is in value space in contrast to quantile space if you are used to ironing in quantile space. And we can talk more about why. Okay. So in this case, here is P, and it's exactly 1/3 P lower plus 2/3 P upper, which will make this revenue 1/3 times the revenue of P lower plus 2/3 times the revenue of P upper, right? And so this is this allocation rule and what it achieves. Okay. So let's go back to our incentive compatibility constraint and see how it comes into play with randomization. So we still want more area under the curve at every bid for day 2 than day 1. And so what we have here is we're posting a price of P on day 1. This is the green curve, it's a price. And what the pink curve does is it's randomizing for an expected price of P. They have the same expected price, but we're randomizing between P lower and P upper. If you want concrete numbers, you can think of P as being 5, P lower being 3, and P upper being 6, right? And so they're both offering an expected price of 5. But this is okay because at every point on the pink curve, there's more area under it than the green curve. So this is fine with our incentive compatibility rule. We can randomize and set the same expected price with the randomization on day 2. However, if we switch it, we're still offering the same expected price. We can no longer do this because it violates our incentive compatibility constraint. Here we have more area under the green curve than under the pink curve, right? So why is this? If you're using that example, you're randomizing over $3 and $6 on day 1 and setting a price of $5 on day 2, then someone with a value of $4 and deadline 2 is going to report deadline 1 because there's a chance that they'll get the $3 option and they can pay for it, whereas they'll never pay for $5 or $6. Okay, so the takeaway here is that if we randomize on day 2, it interferes. On day 1, it interferes with day 2. If we just post the price on day 1 and then randomize on day 2, it was fine. But we need to be careful. There's some asymmetry with the randomization here that we need to worry about when we're solving for the optimal thing. Okay, so one more thing I want to point out is that if you were to just take like the most canonical approach to solve this problem, you might say, okay, what if we just set the best single price? We know that in this case, this was where the day 1 price was cheaper than the day 2 price. Maybe what we should do is just set the best single price. And sometimes that's optimal. But also sometimes you can further optimize on day 2. You know that now you've set this price on day 1, and so for day 2, you can set an even better price. And sometimes that's optimal. But also we now know that we can use the ironed revenue curve and implement points on here. And so if you're trying to set a cheaper price, what you can do is you can randomize over those two peaks, and it's still incentive compatible. And sometimes this is optimal too. And sometimes you might do something else where you fix your price on day 2, and then you further optimize on day 1, and that's optimal. So the only point is that this just looks like a messy case analysis. And the point is that we don't want that. Okay.
Can I ask you a question?
Yes.
Maybe a slide or two ago, you mentioned some conditions that were true under evaluation of expectation. And on this slide, you have a day 1 and a day 2, both with h as the limit. Is it a requirement or meaningful at all to ask whether or not those h's are the same h? These are the upper bounds on the value that somebody could define, right?
We are assuming that they are the same age.
Okay.
Yeah.
So because it might be the case that there are classes of things that I would ship for one day that might have some value that is lower or higher, just sort of ontologically, than things I would ship for
Right.
for longer.
Right. Yeah. Yeah. That's fair. Yeah. Okay.
Organ transplants.
Okay. So what do we do? So again, this is the problem that I told you we're trying to solve, and as you might notice, this is written very much like a linear program. So that's what we do. We write a linear program. So what we're maximizing here is just expected revenue. This quantity phi is the normal virtual value. Just think of it as a constant, as a function of e. And this a is the allocation rule, which is the variable we're trying to set. We're trying to come up with the optimal a variable. Everything else is constants. Okay, but by the payment identity and like known things, this is just expected revenue. Some people are confused. Is that okay?
What is QI and what is FI?
So QI and FI, I said this on like the second slide. This is the probability that we have a customer with deadline I, and then this is the probability of a customer with deadline I having a value of V. Yeah. Okay, so what are our constraints? This one here is our area under the curve constraint. It says that we should report our true deadline over any other deadline. These two here are our feasibility that says that our allocation should be a probability between 0 and 1. And this here is the monotonicity constraint that helps say that we should report our value over any other value. So these are just the same constraints that we already talked about, formulated as a linear program.
Cool.
Yes, it's continuous and infinite. Okay.
What is A prime?
The derivative of A.
Yeah, so the d prime and the v prime are other d, other v, but that's a derivative.
Yeah, that's a, yes. That's completely fair, yes. Okay, so these are alternate deadlines, alternate values. This is a derivative, yes. Okay, good question. I have not noticed that before. Okay, so we can use duality then. We can make some dual variables that correspond to our constraints and formulate the dual. Don't stare too hard at it. The point is just that we formulated a dual. And then you can come up with your, and they correspond back to the primal variables, and you can come up with your complementary slackness conditions. We just went through the normal strong duality proof, and so these are sufficient conditions for optimality. They are not necessarily necessary, but these are the ones we've come up with. And so what we do is we find variables that meet all of the feasibility and optimality conditions, and then that gives that your allocation rule is optimal, and so you have your mechanism. Okay, so just what I want you to take away from that is that we use duality to come up with this system of equations, and then we solve them to find out what the optimal auction looks like. And then it's provably optimal. Okay, so what does it look like in just the case where there are two shipping options, 1 and 2?
No, but why is it a randomized prices? I mean, like what are your...
That's, yeah, hold on.
Okay.
Okay, so right now we're just talking about general A's, right? This is a function. You know, we know that it has to be increasing, but like it could be randomized. So if the allocation is randomized, when we were talking about allocations ruled before, it corresponds to a randomized pricing.
Yeah, because they're composable.
Yeah. Right? We talked about the convex combination of prices. Okay. Okay, so what is the revenue we can get from customers who have a deadline of day 2, given that we set a specific price on day 1? So say this is our price for day 1. What can you do? You know that you need to set a cheaper price on day 2, which would be here, but we also learned that we can use ironing. So actually the best thing to do is just to set the price right there. So we already reasoned about this, which means that we can come up with this function, which is exactly our best price, our best revenue from day 2, given whatever price we set on day 1, right? Because if we set a price over here, then the best thing to do is just to set the best price on day 2, which is cheaper, so we can get this revenue from any point past the best price on day 2, right?
Sorry, will you say that one more time?
Yeah. So if we set a price for day 1 that's to the right of the peak or more expensive than the peak on day 2, then
we'll
we
have
can
to
set the
make
cheaper
sure.
price on day 2 being the best possible price,
Got
which
it.
means we can get the revenue from this point anywhere to the right on it. So now this isn't just price to expected revenue, it's price of day 1 to expected revenue in terms of day 2. We're reasoning about the revenue we can get from day 2 if we set any given price on day 1.
It's almost like a nested gift wrapping problem, or there's some kind of like constraint propagation across each of these price curves that's in terms of what you chose for the one before it. And there's this kind of this ironing that you're doing where you want to wrap on the maxima of that convex shape as much as you can to extract the maximum value here as the seller, right? Is that kind of
From what I understood, yes, but I didn't completely understand that. But we can talk after.
hand wavy.
Okay. Okay. So again, if you're to the right of the peak, then you'll just choose the peak, and you get that revenue, which is why you get this flat line here. And if you're to the left of the peak, then the best thing you can do is choose the best point that's cheaper on it on this ironed curve, which by concavity will be exactly that point. It might be randomized if it's here. If the price for day 1 was here, then it would be deterministic. Okay, so if you set this price on day 1, what you'll do is you'll get the revenue from this point on the ironed curve by randomizing over these 2 peaks. Okay, and so this curve here gives you exactly the revenue when you set any price on day 1, the best revenue you can get on day 2.
Sorry, one quick question. You said that given the price of day 1, we're going to randomize between the 2 peaks, so there's a chance that the day 2 price will be higher.
Yeah, but the expected price is lower. Why does this meet our incentive compatibility? That requires proof. Yeah.
I'll take your
Yeah,
word for it.
yeah.
Okay.
That definitely requires proof. Okay, cool. So the point is just that this curve here is the best revenue from day 2 given a price on day 1. And our revenue curve for day 1 is the revenue from day 1 given a price on day 1. So what it means is we can sum them. And what this curve is just the best revenue you get from both days given a price you set on day 1, which means that the price you set on day 1 should be the peak of this curve, right?
Yep.
Does that make sense? Okay, cool.
So if all the curves were concave, deterministic prices would be optimal.
Yes, exactly. Yes. Okay. So what's the optimal allocation rule in this case? Well, you pick that point, this peak. This is your P, your price for day 1. And if the best day 2 price was cheaper, then you set the day 2 price. We already said this. It's exactly what that pink curve accounted for. And if this is at some ironed point on the revenue curve, then you will use these 2 peaks to randomize and achieve the revenue from that point on the revenue curve, like that. Is that clear? Okay. Cool. So that was just for n equals 2. So how does this generalize to any n? Well, we talked about how to combine this curve for 2 days. We started with day 2, and then we added day 1 on top. You can do this for n. You start with the day n revenue, and then you reason about the revenue from day n given a price on day n minus 1. And you add that on top, and then you can iron it and flatline it to talk about the revenue that you're going to get from the last 2 days given a price you set on the 3rd to last day. Now, you're not just optimizing these, but you're building up these curves that tell you about the revenue you get from the later days given any price you set until you get your curve for what price do I set on day 1 and the revenue I get on all successive days. So what is your allocation rule? You determine it inductively as well. So if you have your curve that tells you your revenue from days 1 through n, it tells you what price to set on day 1. And so we start setting prices that way. If you have your allocation rule, you've already determined your allocation rule for day I minus 1. How do you determine your allocation rule for day I? So this allocation rule breaks down into a convex combination of prices, as we said, with these coefficients. And so for each price, then you look at your revenue curve, your curve that is the combined and iron curve for days I through n. So this is greater than or equal to I is what that's about. You look at the point of that price, and you say, is it ironed there, or is it to the right of the peak? Since it's ironed here, we will pick the best point to the left, which is just at that point by concavity, and so we, again, do the randomization. So you're doing this for every price in the convex combination of prices, which means you're going to end up with at most 2 prices for each of the prices on the previous day, and then you combine them back up, and it gives you your step function. Should I say that again? Yes. Okay. Okay. So we remember that we are getting a convex combination of prices. We have some allocation rule, we decompose it into the convex combination of prices. Here I'm just showing one price. This is one of them. We would do this on every single one. For that price, this is the jth price on day I minus 1. We look at the point of the jth price on the combined revenue curve for days I through n. This is greater than or equal to I, is what I'm using that for. And we say pick the best point to the left of it on that combined revenue curve. It might be the peak if the peak is to the left of it, or it might be exactly at that point if the peak is to the right of it, in which case we will get the revenue from this point, which we do by randomizing over these two peaks. And again, this is not the day I revenue curve. This is that combined curve of days I through n that we talked about building up.
N is the number of shipping options?
Yeah, yeah, exactly. And so what we'll do is we'll just implement the revenue at the best point to the left on this combined curve, which is done by taking those two peaks and randomizing. And so this was just for the jth price. We'll do this for all of the prices in this convex combination, and it'll give, maybe one price, maybe two prices for each of them, right? Because this is randomizing over two prices, which means that when we combine it back up, we get this distribution of at most twice as many prices. Is that okay? Okay. And so the point was just that we took all of our equations and how did we come up with these revenue curves is that they fell out of solving these equations. Okay. So the revenue curves sound like the right thing to do. They sound very reasonable, but to come up with them, we played with these constraints and saw what they had to meet. Yeah. Okay. So the point is that we come up with this optimal clean algorithm for the general FedEx setting with no restrictive assumptions on the distributions, except for the nice continuity stuff, which probably we can relax, although we didn't look into it too much. And it's got this nice inductive structure. And duality was useful not just for proving optimality, as it's often used, but actually for coming up with the structure of this auction. And also, randomization was important in this case, even though we were only dealing with one bidder. In the single item case, you don't need randomization with one bidder. It doesn't come up until there are multiple bidders. But here, because of incentive compatibility, sometimes we need randomization when there are wonky distributions. And again, yeah, no regularity assumptions or other assumptions on the distributions. Okay. So someone already asked this, what's the worst case gap in optimal deterministic? We know it's at worst n because you could just pick the best day to sell to and set that price on all days. And what's the worst case complexity? I said that you at most double the number of prices in the distribution, but we haven't looked into this at all. And just other models for the utility and factoring and costs.
So you don't have any lower bounds on the...
No.
So what does
We-
the split actually mean?
Lower bounds on which?
The first one?
The first one? No, I mean, we just started talking about a lower bound for 2 days this week. So yeah, but in this paper, we don't have any lower bounds, yeah. Cool. Thanks.
I have plenty of questions if you have more questions.
Sorry to run out early. Thank you.
Kira, we'll be around for a few more hours.
Cool, thanks.